Hi, I'm Matthew Giamou, and on behalf of my co-authors, I'll be presenting our work on convex iteration for distance geometric inverse kinematics. We'll begin with a brief description of the inverse kinematics problem our paper aims to solve. Then we'll detail our distance geometric approach, the convex iteration algorithm, and finally present experimental results. Accurate motion planning is essential in any robot manipulation or locomotion task. A robot's forward kinematics are typically simple to compute and describe the effect of control inputs in a robot's configuration space on the end effector's pose in task space. However, the inverse kinematics problem of determining how to make a robot achieve a desired pose in its task space is much harder and far more useful. For many simple robots, IK is a trivial task. However, more complex tree-like or parallel mechanisms can still pose a challenge. This is especially true for IK problems that also include task space constraints like collision avoidance in cluttered environments. To address these challenges, we leverage convex optimization and a distance geometric formulation of inverse kinematics. Let's take a look at exactly what we mean by distance geometric IK. We begin by describing a simple planar robot with control points fixed to joints and the end effector. We can describe fixed link lengths as equality constraints on the squared distance between neighboring points. Similarly, we can describe joint angle limits as inequality constraints on the squared distance between points sharing a neighbor. This relationship between kinematic constraints and distances can be extended to a broad class of inverse kinematics problems for a variety of manipulator types. Fixed link lengths provide exactly known distances. Angular constraints provide bounded distances, and goal poses provide exactly known distances from end effector points to the robot's base. Crucially, all of these approaches lead to descriptions of inverse kinematics that are quadratic feasibility programs. Let's examine how we can solve these quadratic feasibility programs with a method called convex iteration. Consider the simple planar case again, but with the addition of a circular obstacle that the robot cannot collide with. We can relax this quadratic feasibility program to a semi-definite program whose feasible set is the convex spectrahedron pictured here. Observing that the true rank 1 solutions to our original problem are extreme points of this body, we need a way to reliably find these solutions in more complex cases. We begin by modifying the feasibility problem to have a linear cost. At each iteration, we update the linear cost so that it heuristically minimizes the rank of our solution, eventually driving us to a solution that is feasible for our original quadratic program. This convex iteration method was first applied to the noisy sensor network localization problem. Let's examine the performance of CIDGIK on some simulated problems. When applied to popular manipulators avoiding spherical obstacles placed on the vertices of Platonic solids shown here, our method outperforms a standard joint angle encoded optimization approach. The shaded regions indicate end effector pose error of less than 1 centimeter and 0.01 radians. In a more realistic environment with 100 spherical obstacles and a 9 degree of freedom manipulator, the performance gap between our method and the benchmark approach grows. Future work will involve more complex robots and up to thousands of obstacles. Thank you for your interest in our work. Be sure to keep an eye on our GitHub repository for further developments and code releases.